Good morning, everyone. So welcome to my YouTube channel, Maths with Karam. So today we are going to see a lecture on functions of bounded variation. Okay. Let's start today's session now. So I will do one question on the topic done in last lecture. I found that if function f is continuous on closed interval ab and differentiable on open interval ab and its derivative is bounded on open interval ab, then such functions are functions of bounded variation. Okay. So using that result, I will do one question. Okay. Let fx is equal to x square sine 1 upon x if x belongs to open interval 0, 1. Okay. Open interval 0, 1 close. Okay. Open 0, 1 close. Okay. And 0 if x is equal to 0. So my question is f function of bounded variation on closed interval 0, 1, because this function is defined on closed interval 0, 1. Okay. So answer is yes. Answer is yes. It will be. Okay. I will show why it is. So I am going to use a result of last lecture, seventh lecture result. So first of all, what is first of all, you observe that it is continuous on closed interval 0, 1. Okay. So obviously f is continuous on open 0, 1, because on open 0, 1 sine 1 upon x is continuous and x square is also continuous. So fx is continuous on open interval, open 0, 1 close interval. Okay. Now we need to check only x is equal to 0. Okay. So let's check. So what is the limit? X tends to 0 plus fx is equal to limit 0 plus x square sine 1 upon x. Okay. So you see, take its absolute value. Okay. So it is less than limit x tends to 0 plus, because sin x function is bounded by 1. So it will be x square, because sin square function is bounded, since the mode of sin 1 upon x is less than equal to 1. So when I will take less than equal to 1, so it is sin 1 upon is less than equal to 1. I am putting that one here. So it will be x square. X square function is positive, so no need to write absolute here. Okay. So what is the limit of this? This limit is 0. Because I am taking absolute value, so this limit will be also greater than 0. By sandwich theorem, we have limit x tends to 0 plus fx is equal to 0. Okay. So this implies limit x tends to 0 plus fx is equal to 0. But that is nothing but f0. This implies f is continuous at x is equal to 0. So finally, it is continuous on closed interval 0, 1. So this implies f is continuous on closed interval 0, 1. Now, what about differentiable? So I am taking any x in between this. Okay. Then what is the derivative? F dash x. So 2x sine 1 upon x. Okay. Then the differentiation of sine x square 1 cos 1 upon x into 1 minus x square. Okay. After solving it, what you will get? 2x sine 1 upon x, and that is, it will be cancelled out, minus cos 1 upon x. So this implies f dash x is equal to 2x sine 1 upon x minus cos 1 upon x. This is less than 2 times x sine 1 upon x plus cos 1 upon x. Sine and cos are boundations by 1. Okay. So it means, and x is also bounded by 1. Because we have closed interval 0, 1. So it is 2 times 1. Sine is also bounded by 1. And this is 1. So this is 2 plus 1, that is 3. It means f dash x for all x belongs to. Okay. So we have, so this implies f dash exists on open interval 0, 1 and is bounded on open interval 0, 1. Okay. So by result in last lecture, so what we have? Function continuous on closed interval 0, 1. It is differentiable on open interval 0, 1, and it is also its derivative is also bounded on open interval 0, 1. By result in lecture 7 on functions of bounded variation. We get that f is function of bounded variation on closed interval 0 to 1. Okay. So this is done. Now we are going to ask another question, or you can say result. You can say theorem. Let f and g close interval ab to r be function of bounded variations such that there exists a greater than 0 with f gx is greater for all x belongs to closed interval ab. Then f upon g is function of bounded variation on closed interval ab. Okay, so let's prove it. For p is equal to, I'm taking the partition of ab. Partition of ab. We have what we have, f upon g. So what is sp? sp is equal to summation I goes to 1 to n f upon g xi minus f upon g xi minus 1. Now what is this? f xi upon g xi. Okay, minus f xi minus 1 upon g xi minus 1. Okay, so what is this? This is equal to summation I goes to 1 to n f xi g xi minus 1. Okay, minus g xi f xi minus 1 upon g xi g xi minus 1. Okay, okay. So I will add something here and I will subtract something from here. First of all, observe that this is less than equal to I goes to 1 to n. Okay, f xi g xi minus 1 g xi f x I minus 1 k into k. Okay, because this is greater than k, so if I will take k here, this summation will increase because this part is increasing. Because I am taking the lower value, so this summation will increase. So I can take 1 upon k square outside. Okay. So what I am to add and subtract here, okay, accordingly. So what is this? Summation I goes to 1 to n f x I g x I minus 1. So I will add here f x I minus 1 g x I minus 1 here. Okay. And add here same thing, x I minus 1 g x I minus 1, okay, minus g x I f x I minus 1. Okay. Now I will combine these two. Okay, these two, and use triangle inequality. 1 upon k square summation I goes to. I can take gxi minus 1 common from here. So gxi minus 1 is, and this is fx minus fxi minus 1. Okay. And what can I take here from common? F x I minus 1, and that is g x I minus 1 minus g x I. Okay. So this implies SP is less than equal to 1 upon K summation I goes to 1 to n g x I, okay, f x I minus f x I minus 1. Okay, I can take summation. I can distribute the summation separately. Now I can this is f x I minus 1. Now I can write, I can take minus common, then absolute value is here. If I take minus common, so minus will not affect. Either I will write gxi minus 1 minus gxi, or I can write absolute value gxi minus gxi minus 1. Same thing it is. It will not affect anything. Okay. So bracket is closed. So let's say it is equation number 1. Now f and g are functions of bounded variation on closed interval AB. So this implies f and g are, because functions are of bounded variations are bounded. Okay. bounded on closed interval AB. Okay. So this implies there exists K1 and K2. So this implies there exists K1 greater than 0 and K2 greater than 0 such that Fx is less than K1 and Gx less than K2 for all x belongs to closed interval AB. Okay, that's it, equation number. From 1 and 2, we have St is equal to 1 upon K square is already. In this summation, I goes to 1 to and Fxi minus 1 is here, so I can put here K1. And what is this? No, sorry. I should keep it. Let's see the equation number. Equation number 1 again. So I should keep K2 here. K2 Fxi minus Fxi minus 1. I goes to 1 to L. So K1 is here. Gxi minus Gxi minus 1. So this is 1 upon K square. K2 will come out. So this is summation I goes to 1 to L. Fxi minus Fxi minus 1. K1 summation I goes to 1 to L. Gxi minus Gxi minus 1. Okay. So what I will do? What is this? So this will be, because this will be less than Bf. Okay. This will be less than Bg. So this is 1 upon K square K2 Vf plus K1 Vg. Okay. So this implies Sp is less than 1 upon K square K2 Vf plus K1 Vg. But this is finite value. This is finite and fixed. So this implies, so let's say equation number 3. So this is like supremum P belongs to rho AB Sp exists in R. Okay. This implies F quotient G. F upon G is a function of bounded variation on A. Okay. From equation 3, we have supremum P belongs to rho A D S P is less than 1 upon K square K2 BF plus K1 VC. So, FG is function for bounded variation. I'm taking SP functions F upon G. Okay. So this is finite, and we shown that F upon G is function for bounded variation. So we are taking supremum over P partition. So what is this? This is BF upon G. Okay. Is less than equal to 1 upon K square K2 VF plus K1 VG. So this is total variation of F upon G. That is bounded below by this variation. Okay. Variation 1 upon K square K2 times variation of F plus K1 times variation of G. So we'll do 2 questions on this theorem. So first question is that question number 1, question number 2. Let Fx is equal to sine x upon x plus 1. Define on 0, 1. Is F function of bounded variation on closed interval 0, 1? Answer is yes. Yes. Because in last class we have shown that I can write F1. F1 is, let's say, sin x. Sin x is function of bounded variation. Bounded variation on any closed interval. So it is function of bounded variation on 0, 1 also. So let's say F2 is equal to, so this is a polynomial. Polynomial functions are functions for bounded variation. Because this is a polynomial function, so this is functions of bounded variation on any closed interval. So this is function of bounded variation on of closed interval 0, 1 as well. Okay. Now, what is the lower bound for this? Now, observe that F2x, this is, because this function is positive on closed interval 0, so mod will not affect anything. So this function is increasing function. So putting the lower value, it will overall, because I am taking lower value. If I take next value, it will this x plus 1 is actually increasing as positive function. So I am putting the lower value. So it will be x plus 1 will be greater than 1. So this is 1. So this implies F2x is greater than 1 for all x belongs to closed interval 0. Okay. Now F1, F2. Now we have F1 and F2 are functions of bounded variation on closed interval 0, 1, and F2x is greater than equal to 1 for all x belongs to 0, 1. So by theorem of this lecture, we have sin x upon x plus 1. What is that? That is f1 x upon f2x. That is f1 upon f2x is function of bounded variation on closed interval 0. So what does it mean? So it means sin x upon x is, this implies sin x upon x plus 1 is function of bounded variation on closed interval 0. Okay. So now see another question. We have proven just question in the last question that sin x upon x plus 1 is functions of bounded variation on closed interval 0, 1. Now we are doing another question. See this. Question number 3. Let AB belongs to R such that A is greater than B. Okay. Also, let Fx is equal to x upon x square plus 1. Okay. Be defined on AB. Is f function of bounded variation on closed interval AB? Okay. This question I am asking. Okay. Solution. The answer is yes. Yes. Why? Let's see. Because I am taking f1 x is equal to x. Because this is a polynomial, functions of bounded variation. Polynomial functions are functions of bounded variation. Function of bounded variation on AB. Polynomials are functions of bounded variation on any closed interval. Now take this x square. This is also polynomial. So this is also functions of bounded variation on AB. Okay. Now take K is equal to minimum of absolute value of A and absolute value of B. Whether minimum will be greater than 0? Yes. Because A and B are real numbers such that A is still less than B. So both numbers cannot be 0. Both numbers cannot be 0. So their absolute, at least one absolute value of either A or B will be greater than 0. So minimum will be greater than 0. Sorry, 1 minute. Okay. Sorry, let me repeat again. I am taking minimum one. So minimum one will be greater than, I am taking minimum of absolute value of A and B. Maybe one number can be 0 also. So minimum can be 0 also. Or if A and B are not 0, then it will be greater than 0. So ultimately it can be 0. So I will put here sign of greater than equal to 0, because it can be 0 also. Because we do not know whether at least one is 0. Okay. I am saying it A naught. Okay. Now, what is f to x absolute value? So this is a positive function. I can write. Okay. So this is less than equal to, I am taking minimum k naught square plus 1. Okay. Minimum. Because I am taking minimum here, so it will satisfy. For all x belongs to closed interval A. Now take k. Put k is equal to k naught is plus 1. Because k naught is greater than equal to 0, so it is greater than 0. And f to x is greater than equal to k for all x belongs to A. Now we have f1, f2 are functions of bounded variation. And f to x is absolute value greater than k is greater than 0 for all x belongs to AB. Now by theorem, we have x upon x square plus 1 is equal to f1 x upon f2 x, that is f1 upon f2 x is function of bounded variation on closed interval A. So this implies x upon, so this implies fx is equal to x upon x square plus 1 is function of bounded variation on A. So this lecture, up to this, in this lecture we have learned, we have done one question on previous lecture, okay, and we have studied one new result, that is theorem, that if f1 and f2 are functions of bounded variation and gx, absolute value of gx greater than equal to k, where k is greater than 0 for all x belongs to AB. Okay, k is fixed and it is greater than 0, and gx absolute value is greater than equal to k, then f upon g, and it means f upon f quotient g is a function of bounded variation. Using that result, we done two questions, that x upon sin x upon x plus 1 is a function of bounded variation on closed interval 0, 1. We have also shown that, done third example or question, that x upon x square plus 1 is a function of bounded variation on any closed interval. Okay. So in this lecture, we have covered this much matter. Okay. So if you have any program related to this lecture, you can comment me on my YouTube channel. Like, share, comment and subscribe my YouTube channel. So thank you very much for today's lecture.